Okay, good. Thanks everyone for coming, and I hope my audio is coming out okay. So today we are very happy to have Carlo Pagano from Concordia University, that's right, who's gonna speak on the negative Pell equation. Please, Carlo.
Thank you very much, Ramon. I'm very excited to talk at this seminar. Thank you very much for the invitation. So yes, I'm going to talk about a joint work with Peter Koymans, where we recently proved a conjecture of Peter Stevenhagen on the solvability of the negative Pell equation. So roughly, the question that I'm going to discuss, and I will make this precise really in the next slide, is how often the negative Pell equation is solved. So let me introduce the equation. So let's say that I take a square-free integer. Okay, this question actually makes sense also for non-square-free integers, but in today's talk we will focus on the equation for square-frees. A positive square-free integer d, and then the equation star is this one, x squared minus dy squared is -1, and you are trying to solve it with x and y in z. So recall that if you put here a 1, if you do x squared minus dy squared is 1, that's the usual Pell equation, and that's automatically solvable. And typically, as soon as these two is at least 2, there are infinitely many solutions. By the Dirichlet theorem, you can describe them exactly. But the equation star is much more mysterious. So when exactly it's solvable, it's less clear. So the counting function we're going to consider is this Rx. R here is going to be either Z or Q, or maybe some completion of Q, like QP, or the real number. So SRX is the number of D up to X, such that the equation is solvable for X and Y in this ring R. So either in the rationals or in the integers or in some p-adic field. So this equation has a very old history. They are studied since the ancient Greeks, and the Indian mathematicians had already algorithm to solve the classical Pell equations. And the negative Pell equation, though, was studied relatively more recently, and the first sort of foundational result was of Euler and Lagrange, who proved linked the solvability exactly to the parity of the period of the continued fraction expansion of square root d. So the question we are interested in is asymptotic of SZX. So how big is SZX as x goes to infinity? So yeah, there was this criterion of Euler and Lagrange, and first, if you like, lower bound for SZX were proved respectively by Fermat and Dirichlet. So the case with only one prime here is of Fermat, and Dirichlet extended it with 2 primes, but then you have to ask that their Legendre symbol is -1, and they are both 1 modulo 4 in both cases. And then it's automatic, for instance, that D is in SZ infinity. So you see that already here that SZ infinity is an infinite set. It contains these fairly explicit integers. And the question we are interested, though, is what is the correct order of magnitude? Is it much bigger than this? And as I will explain very soon, these examples of Dirichlet were in some sense expected to be 0% in the sense of a conjecture made by Nagel that the relative proportion of the set SCX inside SQX should actually converge to some real number C between 0 and 1, which Nagel in the 30s he did not specify. So C was not specified. And so here, just to remind you, SRX is the set of D up to X for which the equation is solvable with X and Y in R. So this ratio here is the number of D for which the equation is solvable in Z divided by the one for which is solvable in Q. So clearly SCX is inside SQX. And we are taking the probability, the proportion and the conjecture of Nagel that this should have a limiting value. And the limiting value was not even a conjecture for a long time after Nagel. And for a while, even the fact that the lim-inf of SZX divided by SQX was positive was an open problem. So it was not known whether you could, the equation is essentially positive, is solvable positive proportion of the time within the family SQX. And at least people generalized a little bit the criterion, so could do not just with one or two prime factors, but for any number of prime factors, people were able to find some sufficient conditions that were able to give some slightly better lower bounds, but none of this was sufficient at this point to prove that the lim-inf here is positive. So this is a quote from the paper of Cremona and Ottoni. And Valentin Blomer, a few years later, managed to actually at least prove like an effective lower bound for SCX. So sorry, here it should be the cardinality of SCX, which is at least basically x to the 0, x divided by log x to 0.62. And as I will explain in a second, this is essentially 0. The exponent is 0.12 off from the expected exponent. So this is still 0% within SQX. So I will explain this very soon. So this is a quote also from Blomer's paper. So this was the first actual effective lower bound, which was better than all these lower bounds of Dirichlet and Cremona and Ottoni, but was still not sufficient to get the lim-inf being positive. And the reason for this is that the set SQX is a very simple asymptotic formula. It's asymptotic to some relatively explicit constant beta times x divided by the square root of log x. And the reason for this is that D is in SQ infinity if and only if D is in SQ V infinity for all prime V, for all prime V. So this is a theorem of Hasse and Minkowski that a quadratic equation into variables as a solution over the rationals if and only if it has a solution in every completion of the rational for all V place of Q. But now you see that in the equation x squared minus dy squared is -1, all the places that do not divide D basically come for free. If V doesn't divide D, there is a QV point. There is a solution in QV automatically, so V comes for free. So the only requirement is at the V dividing D, and if V divides D, then essentially if V is odd, what you're saying is that x squared is -1 mod V, so to say. So x is basically a fourth root of unity in V. It has order 4, so V must be 1 mod rho 4. So this explains this criteria here, that the criterion here that D is in SQ infinity if and only if all prime factors of D are either the number 2 or they are 1 modulo 4. So it's prohibited to have a prime factor that is 3 modulo 4. Remember, D is square free. So for non-square free, there will be a similar criterion, but you have to ask something about the parity of the exponent. For a square free, so it's very easy to tell from the prime factorization of the discriminant D whether D is in SQ infinity. So the whole point of this story is that for SZ infinity, the criterion is much more complicated, and the question is how to transition from the set SQ infinity to the set SZ infinity. All right, so that shows that this was indeed 0.12 off. So a lower bound of the order x divided by root log x was open for a long time, and also the actual value of Nagel's conjecture, this constant c in Nagel, was not specified, not even in a conjectural form, until 95, when Peter Stevenhagen came with this very weird conjecture that it looks very weird, actually, that the limit of the size of SZX divided by the size of SQX should converge to 1 minus alpha, where alpha is this infinite product, which is not even a rational number. So that's the expansion of 1 minus alpha in a few digits. And despite its weird looking shape, Stevenhagen's conjecture actually came with a fairly sound heuristic behind it. And I will say more about this heuristic when I will introduce more things about SZX and how to verify that something is in SZX. But somehow the heuristic behind this weird looking number is actually was fairly convincing, and also the numerical data was quite fit. So the lower bound situation was finally resolved in a breakthrough paper of Foury and Kluners, which was published in 2010. It's a long series of papers. This was one of the applications, and starting with some papers in 2000, I think, on the 4 rank of class group of quadratic fields. And this negative Pell case was also included, and they were the first one that were able to prove that basically the size of SZX is at least some multiple of x divided by root log x. And moreover, so they not only proved this, so they proved that the lim-inf is bounded away from 0, but they also proved that the lim-sup is strictly smaller than 1. So they got it as a upper bound 2/3 for SZX divided by SQX. So within this very easy family of integers d, such that p dividing d forces p to be either 1 or 2 mod 4, basically. So this is a very easy set, and that's SQ infinity. Within this very easy set, the more mysterious set, SC infinity, you find that the equation is basically solvable positive proportion of the time, and is not solvable positive proportion of the time. And the exact limiting constant remained open in these results. So at this point, we still didn't know that the lim-inf was actually equal to the lim-sup. And the situation remained like this until 2019, where the Stephanie Chan, Peter Koymans, Giorgio Milovic, and myself, we improved the lower bounds. And in 2020, with Koymans, we managed to improve also the upper bounds, upper and lower bounds. And so this was then still the situation for a little while more. And then in 2021, it was uploaded 1 year later, with Peter, we actually proved Stevenhagen's conjecture. So we managed to overcome the difficulties that we were facing when writing these previous works, proving that the limit is exactly what is not only as Nagel's said, but is exactly in the version of Nagel's conjecture predicted by Stevenhagen. So 1 minus alpha is this weird number that appeared in the previous slides, is this infinite product, 1 minus 2 to the 1 over 2 to the j. And so the limit exists, and is exactly as Stevenhagen's conjecture predicts. And from there, and you immediately find as the obvious corollary that you have an answer to the original question. The size of SZX as an asymptotic formula, it's 1 minus alpha times beta times x over root log x, where beta was the counting function for SQX, leading constant for SQX. So okay, that's the main result I will talk about, and let me immediately tell you what the proof was about, and then I will explain what here Smith's method is, and so on. But the main thing is that there were essentially two major stumbling blocks in applying a recent breakthrough from 2017, a series of a paper of Alex Smith on the distribution of to infinity of class groups and segment groups. And when applied to the family SQ infinities, these methods broke down, and we spent a few years trying to find a way around, and that's what we eventually did, and that's what I'm gonna talk about. So I will tell you more about this, and I just want to mention that the same difficulties appears in other sort of seemingly unrelated questions, and one of them is Goldfeld's conjecture about quadratic twists of elliptic curves when they have a rational point of order 4 or a rational subgroup of order 4. And something we're working on with Peter and Mark Schusterman is Chaula's conjecture over FQT, namely for fixed Q, prove the non-vanishing of the L function of a quadratic character at the half point for 100% of the characters. So the current results allow for some proportion, but it's if you fix Q, the proportion is never 1. It's something a little bit smaller. All right, and there are more, and I will just mention these two. And if there are more questions later, I can explain a bit more the connection. So I just want to say here that the difficulties that one finds in tackling this problem using methods introduced by Smith are exactly the same that one faces in negative Pell. All right, so let me now go into a little bit into the strategy of the proof. And to do that, I have to basically start telling you how do you guarantee that a point D, which has these constrained prime factors, they are all, so the question is, when is this point? They're all 1 or 2 mod 4. And the question is, how do we know that the point is in SZ infinity? What is a criterion for that? And to do that, I will introduce the narrow class group. Let me remind you that the narrow class group of the quadratic field Q root D is the group of fractional ideals of the ring of integers divided by the principal ideals that admit, so these are principal ideals that admit a totally positive generator. Totally positive. So this is just a tiny big factor potentially. And we will see whether it's factor or not, then the class group is exactly related with the solvability of the negative Pell equation, but it clearly maps in the usual class group by forgetting this requirement on the positivity of the alpha. And this group has a double face, and for us it's going to be very important that it has two faces. One is as an ideal group, and one is as a Galois group. And it is a consequence of Artin reciprocity law that it's also the Galois group of the maximal abelian extension of Q root D unramified at all finite places. It's a fact that there is a natural identification between this class group and this Galois group. And it's called the Artin reciprocity map, and we are going to capitalize from this double interpretation. Finite places. All right, so that's the class group, and now it is a fairly elementary criterion that D is in S Z infinity if and only if this class square root D, the class generated by square root D, is trivial in the narrow class group. And let me actually very quickly explain it. So this is fairly elementary. So you have square root D. Suppose, okay, saying that the negative Pell equation is solvable, it's not entirely obvious, but one can prove that it's the same as saying that there is a unit of negative norm if the ring of integers would be epsilon bar minus 1, epsilon a unit. If the ring of integers would be 0 D, this would be really a translation of the solvability of the equation, but otherwise you have to be a little bit careful, but you can prove that it's equivalent. Anyhow, so if that's the case, that there is such a unit of negative norm, then this ideal square root D, you can turn it into, you can find a totally positive generator, because now epsilon root D has basically the property that either epsilon root D or minus epsilon root D is totally positive. Totally positive. And the reason is that root D as well is positive in one embedding and negative in the other embedding. So basically this unit epsilon balances this 1 and minus 1. These two signs are balanced by the unit epsilon. So you get either something totally negative and then you negate it, or something totally positive. So you see that you can use a unit of negative norm to turn this ideal into an ideal with, this of course is the same ideal, into an ideal that admits a totally positive generator. And conversely, if there is another generator of this ideal, alpha, that is totally positive, it must change by square root D with a unit, and then basically going backwards in this argument, you find that epsilon bar is minus 1. And so you see that this simple fact is true, that an element D is in S to infinity. We can rephrase at least this by saying that the class of square root D is trivial in the narrow class group. All right, and now what is very important for us is that the narrow class group itself might be a bit too big, and but we know that this class is not just any class; it's actually a two-torsion class, because you have such a thing, and D is certainly totally positive. So square root D square is a totally positive element. So square root D maybe might be non-trivial sometimes, but it's at least always living in the two torsion of this finite abelian group that is the narrow class. And so you see from here that you sort of can cut down a lot the part of the Hilbert class field that you have to consider. You have to take the Artin symbol of square root D, not in the full Hilbert class field, but in the maximal 2 power. Hilbert class field. So essentially what I'm saying here is that the only part of the class group that matters for this problem is the so-called to infinity, the classes in the class group that are killed by some power of 2. All right, so this is going to be absolutely crucial for what I'm going to say. And let me say what's now the outline of the strategy at a very high level. So it is a fact that one can check that D is in SQ infinity, so it's it has this prime factor, so 1 and 2 mod 4. Actually, you can rephrase it by saying that the class of square root d is at least a double in the narrow class group. So it's divisible by 2 in this finite abelian group. And now, using what we have just explained, you can find out that d is actually S z infinity if and only if the class of square root d is a multiple of every single power of 2. So it's in 2 to the s times the narrow class group for all s. So you see that the transition from this set to this set is a sort of infinite process requiring potentially every single power of 2. So to pass from SQ infinity to know that you are actually in SC infinity, you have to essentially check that you are divisible by every power of 2. And that's exactly because square root d is two torsion, because for a two torsion element in a finite abelian group, it's trivial if and only if it's divisible by every power of 2. So now basically the idea is that, okay, now you have this sort of layer, sequence of layers, one for every s, that sort of detects whether you are still divisible by that power of 2 or not. And you can use each layer as sort of successive improvement on your understanding of whether the equation is solvable in Z. And so essentially the plan then is that to get upper bounds, you compute the probability that square root d is in 2, let's say, to the I class plus for I smaller than s, and square root d is not in 2 to the s class plus. So you see this event here, you have managed to survive the first S layer, but the, oh, sorry, S+1. But the S+1 layer, you fail it. For sure, then square root d cannot be 0, because if it's not divisible, 0 is certainly divisible by 2 to the S+1. So square root d cannot be 0, and you have verified it with the power 2 to the S+1. So 2 to the S+1 sort of is witnessing that square root d doesn't manage to have integral solutions to the negative Pell equation. So you do this for every s, and you get better and better upper bounds for SZX inside SQX, and in the end, the plan is basically to get from here that the lim sup is at most 1 minus half. And for the lower bounds, you also have to witness that square root d is a multiple this time. It cannot fail any power of 2. But the class group is finite, so there is some power of 2 that will be enough for every d. And so what you do is you prove that square root d is in 2 to the s times class plus, and 2 to the s times class plus 2 to the s plus 1. So those are the classes in the two torsion that are divisible by 2 to the s equals 0. So if you manage to know both these things, that square root d is divisible by 2 to the s in the narrow class group, and there are basically no other non-trivial two torsion classes divisible by 2 to the s, then the conclusion here is that square root d is trivial in the narrow class group and the equation is solved. So this is contributing to the lower bound. And if you do it for all s, you get better and better lower bounds. And then in the limit, you get the lim-inf is at least 1 minus alpha, and in total you find out that the limit is exactly 1 minus alpha. So that's the very, very basic plan, where you use this criterion here that square root d must be trivial in the narrow class group for the equation to be solvable. You use it, you capitalize on the fact that square root d is 2 torsion, to sort of rewrite this criterion as an infinite process of checks, one for each power of 2. So you do all these checks, and you can use every check to improve your upper bounds and improve your lower bounds, and in the limit you get the desired result. So that's the plan. Now the question is, why is this conceivable? So why is this doable? And the main starting thing is this breakthrough of Alex Smith from 2017, where he basically proved the Cohen-Lenstra heuristics for the 2 parts of the class groups of imaginary quadratic fields. So what he actually got as a result, like what he actually did, was to control this sequence of spaces here, 2 to the s times the 2 to the s plus 1 torsion. So this is the same as the 2 torsion classes divisible by 2 to the s. So these are exactly the things we are looking after here. These are exactly the spaces we are looking after, and we are looking whether it's the case that square root d is in all these spaces here or leaves one of these spaces. And one sort of more conceptual way to phrase this sequence of spaces is that basically you can prove that the full to infinity multiplied by 2 of the class group of imaginary quadratic field follows a conjecture of Cohen and Lenstra, namely the probability that when you order d the natural way up to x, the probability that you get a given finite abelian group is inversely proportional to the size of the automorphism group of A. So the major stumbling blocks that we had, now the idea, of course, once you have such a result and you have such a canon, basically, where you're controlling exactly the spaces you want, you think, oh, okay, now I'm in good shape, I can probably really do something about this. But one of the key problems was that Smith really used it in a crucial way, that the negative of the set SQ infinity, so the set with all prime factors that are 1 modulo 4 or 2, can go in that. He's counting all d up to x, so this is, of course, a set of lower magnitude, but it's not that just he can put them in the error term because it's a thin family. He really has to put them in the error term because the main algebraic results that introduce fail in this family SQ infinity. And another issue is that we don't just need to control. In this very rough plan, you see, I don't just need to control the spaces, I also need to control whether a fixed given class it's in these spaces or leaves these spaces. It turns out that creates quite some difficulties. So the main thing which I will explain, are 2 generalizations that we discovered of a very classical reciprocity law of Laszlo-Redey from beginning of the past century. I will explain much more about Redey's reciprocity and how we generalized it. But for certain objects, which I will also introduce soon, called governing expansions, introduced by Smith, we proved a reciprocity law, and these governing expansions are the key tools that he used in his work, in the algebraic part of his work. And let me mention something here, that in a work in 2019, basically we found that these objects that I will introduce soon are, you can use them to describe the narrow class group of multi-quadratic field Q root D1, Dn, the 2 torsion. These are essentially generators for the they provide a way to describe the two torsion of the dual narrow class group of multi-quadratic field. And I mention this now because this work we did was a generalization of a classical theorem of Gauss, which is about the two torsion of the class group of a quadratic field. So this is a classical theorem of Gauss from his PhD thesis in 1801 from Disquisitiones, which will explain for you why in this theorem here you take the double of the class group. So here the probability that the double of the class group is isomorphic to a given A is as a distribution. The reason is that the two torsion itself of the class group is extremely predictable. So Gauss proved that the two torsion of the narrow class group is generated by the primes, basically the ramified primes in K. So I hope this is readable. You go along all the primes dividing the discriminant, and you have P over P, so you have this relation. Here P square is P is totally positive, mat frac P square, sorry, is P, this is totally positive, so P is clearly, mat frac P is clearly in the two torsion. So these are obvious classes in the two torsion, these ones. And the theorem of Gauss is that basically there are no other classes in the sense that these classes span the full two torsion, and it also tells you how many relations there are. There is exactly one relation. And if you might be tempted for a second to think the relation is square root D, that's exactly what we are after, actually. So square root D is not the relation, because square root is not obviously the relation, because square root D is not as given totally positive. It might be the relation, and whether it's the relation is exactly the negative Pell problem. So the relation is a mysterious product of these primes, which sometimes is square root D, and how often is square root D? It's exactly negative Pell. And Gauss also described, this was all done in terms of quadratic forms, but in terms of modern description, we can say the second part of Gauss units theory is a description of the dual, of the two torsion of the dual. So this V here, I mean the dual group. So maybe I should write it here, A V. For a billion group, I just mean the homomorphism from A in S1 in the unit side. So okay, so the two torsion of the dual, it's basically generated by the quadratic characters coming from Q for the primes dividing the discriminant. Let me explain what do I mean by this. Remember that the class group, we said the class group is also this narrow class group, sorry, is also the Gauss group of the Hilbert class field. So the quadratic characters of this group correspond basically to the unramified quadratic extensions of K that are unramified at all finite places. And now if you have a prime P that divides already D and K is Q root D, you see that, okay, you have to put P star to make sure that it doesn't ramify it at 2, but this extension here, it's this is going to be clearly unramified. Because it doesn't ramify anymore at P, because P here already, the ramification at P is already here. Basically. It's already eaten up there, and you can clearly avoid to ramify it. You are not. You can always represent this extension because it's also equal to square root of D over P star is the same extension. So you in this representation you don't ramify at P. So clearly you don't ramify at P. and these are equal. So these are unramified extensions, and they, by class field theory, by this identification here, they correspond to two torsion classes of the dual. And these are obvious two torsion classes. And again, the statement of genus theory is that they are all. So they are all the two torsion classes are linear combinations of these ones. And now there is a trivial relation, which is that the sum of all of these one is trivial, because the sum of all of these one is the character chi d, the square root of d, which gives you the trivial extension of Q root d. So this is the relation between them. So you see that the two torsion is gigantic. For a typical D, there are lots of prime factors, about log x prime factors. So the two torsion cannot. There is no hope that the two torsion can have any distribution. You cannot say, oh, the dimension of the two torsion it takes every single value with probability zero. So therefore, when you formulate a Cohen-Lenstra for the two infinity, you have to take that into account, and that's why you multiply by 2. And that's why here you control these spaces for S at least 1. So the first space is very explicit, it's gigantic, it has no sort of distribution, and it's a gigantic space. And the key point is that it's extremely explicit. It's very easily written down in terms of the prime factors. All right, so now the question is, how do you go on? So you have these very explicit spaces, and remember, our goal here, our strategy here, is to chase this class square root d in all the powers of 2 to the s. So we need to access the next spaces. We need to know how to control whether square root d is divisible by 4. Or by 8, by 16, and so on. So it's a good start that we know exactly what the two torsion space is. And now the question is how to mechanically sort of move on at the next layers. And here there is a helpful fact that there is a mechanical way, once you know the S space, to describe the S plus 1 space. And this is done as follows. So if I fix a finite abelian 2 group, which for us will be the 2 part of the class group, I define a pairing between the 2 spaces I'm interested in. The 2 to the s, these are the 2 torsion classes divisible by 2 to the s, and these are the 2 torsion dual classes divisible by 2 to the s. And now I pair them. And the pairing is not exactly evaluation of one class in the other, but I write the dual one as I use that is divisible by 2 to the s. So I make a choice here of a psi such that 2 to the s psi is chi, and then I evaluate a psi. And this doesn't depend on the choice of psi, because if you change choice, you will change by psi naught, which with 2 to the s psi naught is 0. If you change the choice, that's the only way to change it. And now a is divisible by 2 to the s, so 2 to the s times b is a. So you can now write psi 0 a is basically 2 to the s psi 0 b, and 2 to the s psi 0 is 0. So this is well defined. It doesn't depend on the choice of the lift psi, and it's a pairing. And what's the point of this pairing? The key point is that the left kernel is the next space and the right kernel is the next space. So the left kernel is 2 to the s plus 1 times a 2 to the s plus 2. By left kernel, I mean the things that vanish with everything else. So in the pairing, the a that kill every single chi. The right kernel is 2 to the s plus 1 times a 2 to the s plus 2. And that's also a fairly elementary thing to check. One direction is kind of obvious. If you're divisible by 2 to the s plus 1, you kill every psi, and the converse, you have to make a little argument. It's not hard. So this is a very formal proposition, but this formal proposition, it's helpful because you see, at the end of the day, we want to chase this space. We want to chase square root d in these spaces. And we have at least a description now by Gauss of the first two spaces. So then we start using this pairing one after the other. So with the first pairing, we can describe the next space, 2 times the class group 4. Then we compute the pairing, we can get the next space, and so on. So basically, we are shifting our question in a question of controlling these pairings and controlling whether square root d is in the left kernel of all these pairings. And let me make a notation for this. I will if A is the narrow class group, I will denote the Artin pairing. This pairing I call it the Artin pairing of level s plus 1 for the narrow class group as art s plus 1 d. And the pairing between x and y, I will denote it by bracket, this bracket here. All right, so that's my notation. Okay, and I will now tell you essentially a result that goes back to still Rayleigh, which is a description of the first two pairings. So the first pairing, which gives you basically the fourth torsion of the narrow class group, is a very classical thing. It's called the Rayleigh matrix, and it's essentially the matrix of Legendre symbols P over Q, where P and Q are prime divisors of D. So this is omega by omega D, where omega is the number of prime factors times omega D matrix, and the PQ entry is P over Q. So it's a symmetric matrix for us because our primes are all 1 and 2 mod 4. So by reciprocity here, you have perfect symmetry because of this constraint modulo 4. And the description of the next pairing, the one that gives you the 8th torsion, it's a bit more complicated and involves something called the Rayleigh symbol. And this is a trilinear symbol that takes A, B, C square free numbers with conditions, and gives you something in F2. And I will tell you more about it soon. Okay, yeah, sorry. So A, B, C are in Q star mod Q star square, and here you have to put a lot of conditions, but I will just call them Rayleigh admissible. The conditions are essentially that the conics, the Hilbert symbols of A, B, A, C, B, C are all trivially all everywhere. There are coprimality conditions. I will not go into the details of this. There are a bunch of conditions. So, but for such a tripole, which is decent, one defines the value of the Rayleigh symbol, which is a bit in F2. So either 0 or 1. And yeah, roughly ABC are pairwise coprime, and like the Hilbert symbols A, B, A, C, and B, C are all 1 for every B. In other words, the conics AX squared plus BY squared is solvable, equals Z squared. The conics AX squared plus BC squared, sorry, plus C Y squared equals Z squared, and all the permutations are also. So the point of the Rayleigh symbol is that first of all, it's a very nice symbol. It satisfies Rayleigh reciprocity, which is saying that the symbol is entirely symmetric and trilinear. And that's non-trivial because the symbol is defined as an Artin symbol of C in an extension that depends on A and B. Some extension that depends on A and B. And this extension is essentially an extension like this, Q root A, root B. And then you take a suitable solution to this conic here, and you do root Z minus root AX. That's a typically D8 extension. And for ABC coprime, pairwise coprime, okay, the Rayleigh symbol is defined also when they're not pairwise coprime, but in this special case, which is enough for us, it's essentially the Artin symbol of C in a field depending on A and B. And so what is surprising is that it's actually entirely symmetric. The definition, it's asymmetric because it's a field constructed in terms of A and B, and then you take the Artin symbol. So here there is some reciprocity going on, telling you that you get the same if you swap the roles. These are the same. Okay, but why do we actually care about the Rayleigh symbol? Remember, I was telling you that the Rayleigh symbol is used to describe the next pair. And the key point is this fact that if you have two divisors that are divisible by 2, then chi A and B, so chi A here is equal to 2 times some function psi, and B is the square of an ideal up to principal ideals, to G. Then the conclusion is that the triple AD over AB is Rayleigh, and the most important thing is that we can compute the pairing between B and chi-A as a Rayleigh symbol. So it's not as simple as the case of Art1, where we simply get a matrix of Legendre symbol. It has a further level of complexity, and it involves this Rayleigh symbol, but we can still write down the pairing between B and chi-A as a Rayleigh. And this Rayleigh symbol satisfies all these nice properties. And essentially, the work of Smith for, in the case of R2, so in a nutshell, so this is the projection on the first coordinates. So it's either P1 or P1 prime, and BD here is, let's say, pi 3 P prime. 0 and T times B0. So essentially the idea of Smith is to work with a cube of fields. So this is a set of 8 possible square free numbers where I change a prime factor in each of these 2 here, so I can form every product here. It would be a square free numbers. These are all pairwise different prime numbers, co-prime to the integer b, b0, and that's you can think of it as a cube of 8 fields. And basically the key relation is this relation star-star, that if you sum the Artin symbol along this cube, you get something that only depends on these primes P1, P1 prime, P2, P2 prime, and P3, P3 prime. And it is simply this Rayleigh symbol here. And let me skip the verification. It is a simple consequence of trilinearity and of the symbol. And the idea now is that we are going to use essentially the following fact. Suppose that you have a grid where you have, basically, you don't know the value you have a function in F2 from the points of this grid to F2. And you don't know individually the function, but you know what the value of the function is when you sum them along every square. You can control what happens to the sum. And that doesn't determine uniquely the function. So you're not able to say something about the function, but the key idea is that for most fillings of the squares, so by putting something here, every single function that sums with that filling is balanced. So in particular, there exists one way to fill these squares in such a way that this is true, that you take value 0 and 1 with roughly the same probability. You can make this quantitative in terms of m, and that's essentially the idea of how to use star star. And the generalization of Smith to higher pairings is to consider higher dimensional cubes, higher version of the symbol, of the Rayleigh symbol, and a generalization of this equation star stars to higher dimensional cubes. And let me not go into the details of the higher Rayleigh symbol, but it's again a symbol that is defined in terms, so you have a field depending on the first s+1 entry, and then you take the Artin symbol of the last one. And the generalization of star star will be basically very similar. You have here P1 of D times H0, PS+2 of D times B0. And then you have these two divisors, and then essentially the star star becomes that the sum over a cube is equal to this higher Rayleigh symbol involving only the moving primes in the cubes. And the major assembling blocks for SQ infinity were that when you would run this equation star star, we call them reflection principles, these relationships between the Artin pairings in these cubes, you would end up with the Artin symbol of infinity in a field depending. Basically, you were checking whether a field depending on the first on these s+1 primes is totally real. A field LP1, P1 prime, PS+1, PS+1. So the key point in carrying out this combinatorial idea is to invoke Chebotarev density theorem on P3 prime, and here you get instead, as a result of this thing, the behavior of infinity in a field that is depending on the cube. So that is not very helpful because there is no Chebotarev density theorem in a setting like this. And even worse, since you are in SQ infinity, when A is equal to B, which was prohibited in this setup, A here was quite different from B. A was supported here and B was supported here. When A is equal to B, then you get the Artin symbol of A in a field depending on A. So that's kind of a nightmare. That's not something you can apply any Chebotarev on, as it is. And yeah, so that's where, when I said Smith really put in the error term this SQ infinity, is exactly because essentially he wants that for a generic D, the first space already has A and B basically disjoint. So there is the set of A and B do not overlap. So a set like SQ infinity is very bad because one can check that the first space of SQ infinity, the set of A and B coincide. So in SQ infinity, you always have to consider from the start that sometimes A is equal to B, and you have to pair A with itself. And the way out of this, and that's the end of this talk, were two reciprocity laws. So for these higher array symbols, one reciprocity law is essentially that you can swap the first, the last two entries, and the result is the same. That's a generalization of Radey's reciprocity. And that's very good, because then I can swap these two. And I can basically apply, I can use these as a Chebotarev prime, and I can carry out this combinatorial strategy here. And the other one is even trickier. Essentially, what we had to prove is that for the higher array symbol with equal final entry, the final result is 0. And the way you can use this to apply Chebotarev to the pairing of A with itself is a bit complicated to explain, but I'm happy to say more if there are questions on this. And yeah, I think that's a good place where to stop.
Okay, so my internet made me come back right in time for thanking you. I'm not sure. Can you hear me? Or?
Yeah, I can. Hi.
All right, good. My internet went down just before you finished. So, it's good that you didn't drop everyone. Anyway, good. Thanks a lot. I enjoyed the talk. And does anyone have a question? Okay, maybe I have a naive one. So, isn't it natural to ask about solutions to x squared minus dy squared equals to a, where a is different from plus or minus 1?
Oh, yeah, that's a very natural question. And so if, let's say L is a prime, just to make it slightly simpler. And if L is a prime and it's a 3 modulo 4, we have a preprint where we computed the analog of this.
Okay.
And for 1 modulo 4, at the moment, we have no idea how to do.
Okay.
Somehow there are in this strategy extra problems where this thing here is not even enough. So yes, it's in principle one would like to do it for any fixed data.
I see. Yeah. That's nice. So, anybody else? No? Okay, so I invite everyone to thank Carlo again. Wait.